This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 18, Quantum Vibration and Rotation of Molecules, Sections 18.1 and 18.3, the classical and quantum mechanical harmonic oscillator. First, let's define the harmonic oscillator. The potential energy of a harmonic oscillator is half kx squared. K is the force constant. X is the displacement. Hooke's law states that the force exerted to a spring is proportional to its displacement. They have the opposite directions. Therefore, force is equal to negative kx. K is the force constant. Also, we know force is equal to negative dv over dx, where v is the potential energy. And therefore, we have dv over dx is equal to kx. We can move this dx to the right-hand side and integrate both sides. We get vx is equal to half kx squared. The potential energy of a harmonic oscillator is half kx squared. Now we can derive the vibrational frequency of this harmonic oscillator. Newton's law, F equals ma. A is the second derivative of the displacement with respect to time. F is also equal to negative kx. So this m times a, or second derivative of x, is equal to negative kx. And then we move this m to the right-hand side. The second derivative of x with respect to time is negative k over mx. We solved this kind of equations before. This is the general solution. It's a linear combination of e to the power of positive I times square root of k over m times t, and e to the power of negative I times the square root of k over m times t. Remember, e to the power of I theta is cosine theta plus I sine theta. So we can change this exponential functions to cosine and sine functions. Note that this C1, C2, B1, B2 can all be complex numbers. We can also combine these two terms and then get this. It can be a sine function of the square root of k over m times t plus alpha. Alpha is the initial phase of this angle. The square root of k over m is the angular frequency. The angular frequency is 2 pi times the ordinary frequency. Now let's evaluate the period of the oscillation. So this uppercase T is the period of the oscillation. Because this is a periodic function, we have this equation here. If we have this time t plus 1 period of oscillation, we should have a difference of 2 pi. So if we compare this and this, the difference should be 2 pi. This is because the period of a simple sine function, sine theta, is 2 pi. By solving this equation, we cancel this lowercase t and this lowercase t. We learn this period of oscillation is 2 pi times the square root of m over k. And also, we can rewrite this displacement of the spring to be this sine function or this sine function. Sine of 2 pi multiplied by time over 1 period of oscillation plus the initial phase. Once we have the period of oscillation, uppercase t, we can take its reciprocal to get the frequency. So the frequency is 1 over 2 pi times the square root of k over m. What about the angular frequency? The angular frequency omega is 2 pi times the ordinary frequency. So the angular frequency is simply the square root of k over m. So right here, you are looking at the angular frequency in front of time. What if you have a two-body harmonic oscillator, such as a diatomic molecule? We can separate the translational motion of this molecule from its vibrational motion. It is possible. We can solve the Schrodinger equation for the pure vibration of the diatomic molecule without worrying about its translation. To do that, we simply solve the same equation, except one thing. We need to replace the mass of the one particle in the one particle problem M with the reduced mass of two particles mu for this two-body system. 1 over mu is equal to 1 over m1 plus 1 over m2. The reciprocal of mu is the sum of the reciprocal of m1 and the reciprocal of m2. Mu is always smaller than m1. Mu is always smaller than m2. Now let's do some mathematical derivation. When we have a two-body system, we can define the center of mass. And then this uppercase M is the sum of the two masses. This V is the translational velocity. And this is the weighted velocity, the mass-weighted velocity. We can easily prove that the kinetic energy in this system is equal to the kinetic energy in this system. On the left-hand side, you have the kinetic energy of mass 1 plus the kinetic energy of mass 2. On the right-hand side, you have the translational energy and vibrational energy. V2 minus V1 is the relative speed between these two masses. And this tells you how fast the vibration is. And then this mu, again, is simply m1 times m2 over m1 plus m2. Or you can say the reciprocal of mu is the sum of the reciprocal of m1 plus the reciprocal of m2. We can prove this. We start from the right-hand side over here. We plug in this uppercase M is equal to the sum of the two masses. We plug in this mu as m1 times m2 over m1 plus m2. And then we do the derivation. It's tedious, but it's not too difficult. As long as you are careful, in the end, you will prove that the sum of the translation energy and vibration energy is the sum of the kinetic energy of mass 1 and the kinetic energy of mass 2. We mentioned diatomic molecules, but the potential energy surface of a diatomic molecule is not exactly quadratic. So over here, you are looking at the harmonic oscillator. This yellow line is harmonic. The red line is the real diatomic molecule. They are different. However, if the bond distance is very close to the equilibrium bond distance in this region, I think we can safely use the harmonic oscillator model to describe the diatomic molecule. Again, around this region, the yellow line matches with the red line fairly well. So how do we solve the Schrodinger equation for the diatomic molecule? Well, again, this is the Schrodinger equation. Again, all you need to do is you need to replace M with mu, and in this case, mu is the reduced mass of the two atoms in this diatomic molecule over here. If you're looking at a molecule such as HCl or HBr, because H is much lighter than Cl or Br, the reduced mass of such a molecule is very close to the mass of hydrogen. In general, mu is very close to the mass of the much lighter atom. Now let's look at the solution of this. I'm not going to solve this. It's solved by mathematicians. It's not a trivial task to solve this from the beginning. So I'm going to just give you the solutions. The solutions look complicated enough. We have a coefficient here. This is normalization factor. We have a polynomial function here in this form. and then we have a Gaussian function here. Now let's explain. This is to make sure the probability of finding the displacement from negative infinity to positive infinity is 100%, right? And then this is a polynomial function. We're going to come back to this later. This is a Gaussian function. This alpha is the square root of k times mu over h bar. K is the force constant. Mu is the reduced mass. Well, you can see the unit of alpha should be meter to the power of negative 2. Again, this should be e to the power of a number. This is the formula for the normalization factor. It's 1 over the square root of 2 to the power of n times n factorial times alpha over beta to the power of 1/4. You can plug in n equals 0 here. It's going to be just 1 over 2 to the power of 0 times 0 factorial. So this part is 1. And then a sub 0 is simply a alpha over beta to the power of 1/4. Again, this h is a polynomial function. It's the Harmonic polynomial function. It has this kind of form. It looks a little complicated, but really you just need to evaluate the derivative of this Gaussian function. Multiply that by this e to the power of x squared over 2 and multiply by this plus or minus sign. That's it. What if n is 0? When n is 0, you simply just do not evaluate its derivative. When n is 0, you have d to the power of 0 over dx to the power of 0. So this part is 1. And this part cancel with this part. You get 1. Negative 1 to the power of 0, that's 1. So when n is 0, this Harmonic polynomial function is simply 1. Now, what if n is 1? Well, in that case, you need to evaluate the first derivative of this. Well, it's going to be just simply negative x times this Gaussian function. And then negative 1 to the power of 1 is negative 1. You have two negative signs, one here, they cancel. And this guy cancel with the Gaussian function. So in the end, it's going to be x when n is 1. So you see x here when n is 1. Anyway, you can easily evaluate this for n equals 0 or 1 or 2 or 3, etc. And then you can get this solutions to the Schroding equation of vibration. All right, again, this is just normalization factor. And 1 is the polynomial function here. X is the polynomial function here. This is the polynomial function, and this is the polynomial function. And over here, we have the Gaussian function, Gaussian function, Gaussian function, Gaussian function. So they share a common factor, which is the Gaussian function. And again, this alpha is the square root of k times mu over h bar. All right. In the ground state, that means the lowest energy state, we have this wave function. Let's not worry about the normalization factor. It's not quite important. The major use of the normalization factor is to make sure the total probability is 100%. All right. Later, when you learn molecular orbitals, you will see the normalization factors for the atomic orbitals are also important. They show us the relative contribution from those atomic orbitals. But for now, it's unimportant to include the normalization factor. So let's just focus on this. All right. Let's look at the Hamiltonian operator. It's just over here. On the left-hand side, you have kinetic energy operator plus the potential energy operator, right? And then on the right-hand side, we just plug in this psi. All right. So psi is plugged in. All right. And then what we need to do is we need to evaluate this. And in the end, we will get the original wave function as part of the result. The result is going to be this wave function multiplied by a constant. And that constant is supposed to be the vibrational energy. All right. Again, alpha is the square root of k times mu over h bar. So we just evaluate the second derivative. So the first derivative is this. And then this is the second derivative. We take care of the coefficients. We calculate, derive every single step carefully. So anyway, in the end, you will get this as the final expression. which is the wave function, the original wave function over here, multiplied by a constant. This constant is just 1/2 h bar times the square root of k over mu. Alright, so this h bar is h over 2 pi. So we can also write this as 1/2 h nu, and this nu is 1 over 2 pi times the square root of k over mu. Alright, so that's the frequency of the classical harmonic oscillator. Okay, so again, I would recommend you to derive this yourself. It's tedious, but if you are careful enough, you will be able to get the same result here. The vibrational energy is half h nu when we are looking at the lowest possible vibrational energy level, when we are using the ground state wave function, this one. Alright. By the way, if you use this wave function, you will get 1.5 h nu. If you use this function, 2.5 h nu, this function will give you 3.5 h nu. Now let's get back to the normalization factor. Let's say we put the normalization factor here, and then it will appear here and here. It will appear here and here, here and here, here and here, here and here. But in the end, the normalization factor will appear inside this parenthesis and here and here. So by adding the normalization factor in the wave function, we get the same result, the same eigenvalue. You're going to see the eigenvalue is still 1/2 h nu. The normalization factor will be inside the parenthesis as part of the normalized wave function. Again, in classical mechanics, we learned the frequency of the harmonic oscillation is 1 over 2 pi times the square root of k over mu. We see that same expression here. Okay, over here, this is for quantum mechanical oscillator. So the frequency depends on the force constant and the reduced mass. The larger the force constant, the higher the frequency. The lower the reduced mass, the higher the frequency. So if you have learned infrared of some functional groups in organic chemistry, you'll see if you are talking about a bond between a hydrogen atom and any other atom, usually you'll have a fairly high frequency because the reduced mass of HCl, HBr, HF is very small. You have a small mu, you have a higher frequency. When you have a higher frequency of this harmonic oscillator, well, you will see higher wave number in the infrared spectrum. But on the other hand, if you're looking at bromine 2, well, they have a really large mu, and then you will see very small frequency and small wave number in the infrared spectrum of HBr. And also, when you are collecting infrared spectra, sometimes we use salt plates, sodium chloride or potassium bromide, because potassium bromide has a heavier reduced mass than sodium chloride. KBr has a lower infrared wave number than sodium chloride. Now let's get back to the K. So if we're looking at the force constant, we can actually look at the infrared wave numbers for carbon-carbon single bond, double bond, and triple bond. Carbon-carbon single bond has a wave number of roughly 1200. Double bond 1600, triple bond 2100. So the higher the force constant, the higher the frequency. By the way, force constant and bond energy are not the same thing, but we can prove that the force constant is approximately proportional to the bond energy. All right. Now let's get back to the wave function. This is the normalized wave function. For the lowest vibrational energy level, we have the normalization factor here. It looks a little complicated, but essentially you just need to know it's a Gaussian function. And the exponential coefficient here is negative alpha over 2. And alpha is the square root of k times mu over h bar. Alpha has a unit. The unit of alpha is meter to the power of negative 2. In general, the vibrational energy levels are n plus half times h nu. N can be 0, 1, 2, and 3, so it's going to be half, or 0.5, 1.5, 2.5, 3.5, etc. And this nu is 1 over 2 pi times the square root of k over mu. This equation is exactly same as the equation for the classical harmonic oscillator. Now let's look at the tunneling effect. So when we are doing vibration, we can observe tunneling effects. So that means this is the potential energy. This is the potential energy. And now, what if the particle has lower energy than the potential energy outside this potential energy curve? We can see the wave function is non-zero. That means it's possible to observe the particle outside this, well, I'm going to call this a curvy one-dimensional box. All right, a curvy box, okay? This is a curvy box. So the particle can appear outside this curvy box with a negative energy, and that is fine. So over here in this region, it has a negative kinetic energy. This region, and this region. Okay? When the particle has higher energy, so this is a higher energy, this is lower energy. When the particle has higher energy, we have a more significant tunneling effect. All right? So again, this is the wave function. Over here, this is the squared modulus of the wave function. So all these function values are positive, and the squared modulus of a wave function is the probability density. Again, it can be non-zero. It's positive outside this curvy box. The particle may appear in a region with negative kinetic energy. It's called classically forbidden region. But there's one thing I have not mentioned before. It's okay to have a negative kinetic energy in this region and in this region. But the overall expectation value of the kinetic energy has to be non-negative. So we got this region, they have negative kinetic energy, but in this region we have positive kinetic energy. If we look at the probability weighted kinetic energy, we take this part, and this part into account. Overall, the expectation value of the kinetic energy should always be non-negative. In this case, it's always positive.